Let's now look at a couple of concrete examples of schedulers that are part of an actual operating system. First, we will look at the so-called O of 1 scheduler in Linux. The O of 1 scheduler receives its name because it is able to perform task management operations, such as selecting a task from the run queue or adding a task to it, in constant time, regardless of the total number of active tasks in the system. It's a preemptive and a priority-based scheduler, which has a total of 140 priority levels, with 0 being the highest and then 139 the lowest. These priority levels are organized into two different classes. The priority levels from 0 to 99 fall into a class of real-time tasks, and then all others fall into a so-called time-sharing class. All user processes have one of the time-sharing priority levels. Their default priority is 120, but it can be adjusted with a so-called nice value. There's a system call that can be used to do this, and the nice values can be between -20 and 19, so as to span the entire set of time-sharing priorities. The O of 1 scheduler borrows from the multi-level feedback queue scheduler in that it associates different time slice values with different priority levels, and it also uses some kind of feedback from how the tasks behaved in the past to determine how to adjust their priority levels in the future. It differs, however, in how it assigns the time slice values to priorities and how it uses the feedback. It assigns time slice values based on the priority level of the task, similar to what we saw in the multi-level feedback queue scheduling. However, it assigns smallest time slice values to the low priority CPU-bound tasks, and it assigns high time slice values to the more interactive, high priority tasks. The feedback it uses for the time-sharing tasks is based on the time that the task spends sleeping, the time that it was waiting for something or idling. Longer sleep times indicate that the task is interactive. It spent more time waiting, for instance, on user input or on some type of events. Therefore, when longer sleeps are detected, we need to increase the priority of the task, and we do that by actually subtracting 5 in particular from the priority level of the task. In this way, we're essentially boosting the priority, so next time around, this interactive task will execute with higher priority. Smaller sleep times are indicative of the fact that the task is compute-intensive. Therefore, we want to lower its priority, and we do that by incrementing it, by adding the number 5 to it up to a maximum. And essentially, the task next time around will execute in a lower priority class. The run queue in the O of 1 scheduler is organized as two arrays of task queues. Each array element points to the first runnable task at the corresponding priority level. These two arrays are called active and expired. The active list is the primary one that the scheduler uses to pick the next task to run. It takes constant time to add a task, since you simply need to index into this array based on the priority level of the task, and then follow the pointer to the end of the task list to enqueue the task there. It takes constant time to select a task because the scheduler relies on certain instructions that return the position of the first set bit in a sequence of bits. So if the sequence of bits corresponds to the priority levels, and a bit value of 1 indicates that there are tasks at that priority level, then it will take a constant amount of time to run those instructions to detect what is the first priority level that has certain tasks on it. And then once that position is known, it also takes a constant time to index into this array and select the first task from the run queue that's associated with that level. If tasks yield the CPU to wait on an event or are preempted due to higher priority task becoming runnable, the time they spend on the CPU is subtracted from the total amount of time, and if it is less than the time slice, they are still placed on the corresponding queue in the active list. Only after a task consumes its entire time slice will it be removed from the active list and placed on the appropriate queue in the expired array. The expired array, that contains the tasks that are not currently active in the sense that the scheduler will not select tasks from the expired array as long as there are still tasks on any of the queues in the active array. When there are no more tasks left in the active array, at that point, the pointers of these two lists will be swapped, and the expired array will become the new active one, and vice versa, the active array will start holding all of the tasks that are removed from the active array and are becoming inactive. This also explains the rationale why in the O of 1 scheduler, the low priority tasks are given low time slices and the high priority tasks are given high time slices. As long as the high priority tasks have any time left in their time slice, they will keep getting scheduled. They will remain in one of the queues in the active array. Once they get placed on the expired array, they will not be scheduled, and therefore we want the low priority tasks to have a low time slice value so that, yes, they will get a chance to run. However, they won't disrupt the higher priority tasks. They won't delay them by too much. Also note that the fact that we have these two arrays also serves like an aging mechanism. So these high priority tasks will ultimately consume their time slice, be placed on the expired array, and ultimately the low priority tasks will get a chance to run for their small time amount. The O of 1 scheduler was introduced in the Linux kernel 2.5 by Ingo Molnar. In spite of its really nice property of being able to operate in constant time, the O of 1 scheduler really affected the performance of interactive tasks significantly. And as the workloads changed, as typical applications in the Linux environment were becoming more time sensitive, think Skype, movie streaming, gaming, the jitter that was introduced by the O of 1 scheduler was becoming unacceptable. For that reason, the O of 1 scheduler was replaced with the completely fair scheduler, and the CFS scheduler became the default scheduler starting in the Linux 2.6.23 kernel. Ironically, both of these schedulers are developed by the same person. You should note that both the O of 1 and the CFS scheduler are part of the standard Linux distribution. This one is the default. However, if you wish, you can switch and choose the Linux O of 1 scheduler to execute your tasks.